Hey guys, it's Miss Rainey. Welcome back to Chemical Foundations. In this video, we are going to be looking at the metric system and conversions. We're going to be looking at dimensional analysis or factor label. We're going to be looking at density, and we're going to be looking at different temperature measurements. I hope you are excited like me and you are ready to get started. Let's go. Okay, so first of all, just want to look at a couple of metric system prefixes and common conversion factors. Sometimes these will be given, sometimes these will be not. There are a few that you really should memorize. So let's talk with the metric system, the ones that you want to memorize. In the metric system, there is a base unit, which is a meter or a liter or a gram. If you go 1,000 base units, then you have a kilo. If you have a million base units, then you have a mega. If you have a billion base units, then you have a giga. But you can also go the other direction, so that if you have 100 centis, then you will get one base unit. So these are lower than a base unit. Or 1,000 millis, you get a single base. Or 1 million micros, and you get one base, that kind of thing. And then these common conversion factors, for the most part, you won't have to memorize, but there are a couple that you really should be aware of. That is, a milliliter and a cubic centimeter are the exact same thing. They have the exact same measurement. They are the exact same thing. The most common ones we're going to use from metric to common conversion factors are an inch to centimeters. Every once in a while, you'll go grams to pounds or pounds to kilograms, something like that. These common conversion factors will be given. You don't have to memorize, but you just need to know how to use them. So let's talk about how to use them. This is a process called dimensional analysis. Some people call it factor label. It's a method of converting a measurement in one unit to another unit by multiplying a quantity by a conversion factor so that the undesired unit cancels. So then a conversion factor is created from an equivalency and it's always equal to 1. So if I gave you this math problem here, I said, what is 1 divided by 1? Hold on. Let me put that in regular pen, not highlighter. What if I said 1 divided by 1? Then you would say, oh, well, that answer is obviously 1. And if I said 12 divided by 12, you would say, well, that answer is obviously 1. But then some people get confused when I say, fine, 12 divided by 12 is 1. What about 12 inches divided by 12 inches? Well, the trick to that is that is also equal to 1, because the 12s cancel out, but the inches also cancel out, and we get 1. But what if I did something even weirder and said 12 inches divided by 1 foot? 12 inches and 1 foot are exactly still the same thing, so it is still equal to 1. So a conversion factor is dividing two numbers by the exact same thing, like dividing two numbers by themselves, and then you still equal 1. So 2.54 centimeters in an inch is equal to 1. Or 1 inch over 2.54 centimeters is equal to 1. These are conversion factors. They are the same value on the top as on the bottom. So if I wanted to use one of those conversion factors, say how many inches are there in 31.8 centimeters, I'm going to start with the number that I know, 31.8 centimeters. And I'm going to multiply that by one of these conversion factors so that the undesired unit cancels. So since I have centimeters to start with, I'm going to put centimeters on the bottom to get it to cancel, and I am looking for inches. But in order for this dimensional analysis to work, I need to put equivalent numbers on the top and the bottom. So say 1 inch is 2.54 centimeters. So 31.8 divided by 2.54 times 1 is 12.5. And so then for my units, the centimeters divided by centimeters cancels. I'm left with inches. And that's dimensional analysis. So let's make that a little bit trickier. What is the weight of a 2.3 pound pineapple in milligrams? So these conversion factors are given. I just have to know how to use them. I'm going from pounds to milligrams, so I see that I can go from pounds to kilograms, and then I can go from kilograms to milligrams. So I'm going to start with pounds to kilograms. I've got a 2.3 pound pineapple. I'm going to multiply by a conversion factor with the unit I'm getting rid of on the bottom, the unit I am looking for on the top, and equivalent amounts between them. So there's 2.2 pounds for 1 kilogram, so I'm going to write 2.2 pounds for 1 kilogram. I'm just filling in the equivalent amounts from the chart. Trick is that's kilograms, and I don't actually want kilograms, I want milligrams. So I'm going to remember my metric prefixes and say that there are 1,000 base unit grams in 1 kilogram. And if I can cancel out the grams and turn it to milligrams, there are 1,000 milligrams in 1 base unit gram. And so now I'm going to solve. Notice that we are multiplying each of these times, so I'm going to take 2.3 times 1 divided by 2.2 times 1,000 divided by 1 times 1,000 divided by 1, and I end up with the number 10454.545. Oh, that's a lot of significant figures. And then I'm going to round that because that's way too many. I have 2.3 pounds. This is entirely multiplying and dividing, so I want 2 significant figures. My 2 significant figures are these first 2. So I'm going to put that in scientific notation, 1.0, so I get 2. 1, 2, 3, 4, 5, 6 times 10 to the 6. The next most important part is the units. Pounds cancel, kilograms cancel, grams cancel. We're left with milligrams. 1.0 times 10 to the 6 milligrams. You could not say, what is this? Nope. 1 million milligrams, because 1 million has only one significant figure, and we need 2. Okay, let's try another one. The volume of a solid is measured by water displacement when the solid is placed in a graduated cylinder containing 20 milliliters of water. So let's just say we've got 20 milliliters of water in this graduated cylinder. Then the solid is placed into it. There's my solid. And the water level rises to, let's say, 23.2 milliliters once I've added my solid into it. So now I want to find the volume of the solid in cubic inches. So the first thing I want to do is figure out the volume of my solid in milliliters, because those are the numbers I already have, so I'm going to subtract. That gives me 3.2 milliliters. So the volume of my solid is 3.2 milliliters. But I don't want milliliters, I want cubic inches. So first of all, I have to remember that a milliliter is the same as a cubic centimeter, and then I can convert centimeters to inches. So 1 milliliter is the exact same thing as 1 centimeter cubed. And then we're going to cancel centimeters by putting it on the bottom. And my conversion chart says 1 inch is 2.54 centimeters. But there's a problem with my units, because a centimeter is not the same thing as a cubic centimeter. So let's look at this little box down here. And so if I zoom in on my little box, let's see what I've got. Let's pretend that this box is 1 inch cubed, which means it is 1 inch by 1 inch by 1 inch. So if we were thinking about cubic centimeters, this is going to be 2.54 centimeters by 2.54 centimeters by 2.54 centimeters. So for 1 inch cubed, 1 times 1 times 1 is 1 inch. But for my centimeters, it's 2.54 times 2.54 times 2.54, which is really 16, let me see, 0.39 centimeters cubed. So even though 1 inch is the same as 2.54 centimeters, 1 inch cubed is the same as 16.39 centimeters cubed. So now let's go back to this problem up here. We can't just say 1 inch and 2.54 centimeters. Instead, we are talking about an inch cubed. So that's 1 cubic inch. And we're going to cube the number, and we're going to cube the unit. 1 cubic inch and 2.54 cubed centimeters cubed, which is essentially the same thing as 16.39 0.39 centimeters cubed. So we are cubing the number and the unit. And that way our units, centimeters cubed, will cancel with centimeters cubed. We will have inches cubed left over. So I'm going to take 3.2 and I will divide that by 2.54 cubed, and I end up with 0.1953, rounding that to two significant figures, 0.20 centimeters, inches cubed. There we go. All right, let's try another one. A car is driving down a residential street at 30 miles per hour. How many feet is that car traveling every second? So this one is funny. MPH is miles per hour. So it's 30 miles per every 1 hour. This is a double unit, a miles and an hour. We want to change the miles to feet, and we want to change the hours to seconds. So we have two separate types of conversions that we're going to do. And we can start with miles is fine. Miles turning into feet, and my conversion says that there are 5,280 feet in 1 mile, and that will cancel my miles and leave me with feet, which is what I'm looking for, so my distance is good. Now we're looking for time. For hours and seconds, I didn't write that conversion on your chart. I just hope that you know that an hour has, and if you can't go to seconds, go to minutes. 1 hour has 60 minutes in it. And so my hours will cancel and leave me with minutes. I don't want minutes, I want seconds. Hopefully you are aware that 1 minute has 60 seconds. So my minutes will cancel, and I'll be left with seconds. So in this case, I'm canceling from top to bottom, bottom to top instead of top to bottom. But either way, I'm canceling. What I don't want, I'm going to put on the other side of the fraction. As far as my calculations, 30 times 5280 divided by 60 divided by 60. 30 times 5280 divided by 60 gives me 44 for the units, feet per second. 44 feet every single second when you're driving down a residential street is excessively fast. Imagine a small child running out in front of your car. Do not drive that fast down a residential street because you will be going 44 feet in 1 single second. Okay, so now let's look at density. Density is an object's mass compared to its volume or divided by its volume. So density is mass over volume. D is m over v. So let's say a student is trying to determine the density of some sort of unknown liquid. The student places a graduated cylinder on a balance and determines its weight is, and I'm going to put a weight in here, 0.2, nope, that is wrong. Let me reread that. That is 112.3 grams. And then they place liquid in the cylinder. Okay, so now there's some liquid in the cylinder. And now it weighs 129.7 grams. And my volume is 20.22 milliliters based on the precision of my instrument. Step 1, how many grams is that? 129.7 minus 112.3 gives me 17.4. This is the correct number of significant figures. It has one place past the decimal, and when I'm subtracting, I'm looking at places past the decimal. So I have 17.4 grams, and then 20.22 milliliters for my volume gives me 0.86. And that's 0.861 grams per milliliter. But when I'm looking at my chart, the closest to that looks like toluene. So I have toluene, which is cancerous, so please don't be measuring toluene, U-E-N-E, as my unknown liquid. There we go. So now let's say a student wants to collect 350 grams of diethyl ether. So diethyl ether, that's going to be this one with this density of grams per centimeters cubed or grams per milliliter. And so what size beaker should be used? So what size beaker? means that I am looking for the volume of the beaker. I have the mass, I have the density. So since I have mass of 350 grams, and since I have density of 0.714 grams per milliliter, I'm going to take my volume and take my mass divided by my density. Volume is mass over density. I'm rearranging by multiplying both sides by volume and dividing both sides by density. 350 grams divided by 0.714 grams per milliliter gives me 490 for my number, let's say 0.2. For my unit, the grams cancel, and I'm left with milliliters on the bottom of the bottom, which means milliliters is on the top. By the way, that's not the size of my beaker. This number here is 490.2 milliliters. But my beaker needs to be a bit larger than that. I don't want my liquid to fall out of it. So I need a beaker that is at least 500 milliliters or larger. But you're not ever going to find a beaker that holds exactly 490.2 milliliters. We need something that size or bigger. All right, here's another density question. What's the mass of 1.25 quarts of isopropyl alcohol? So this time we are looking for mass. So I have a density triangle that may be helpful to you. I don't know if you've seen this before in, say, a junior high class where we have density, mass, and volume. Mass is on the top, density and volume are both on the bottom. If we are looking for, let's say, mass in this case, and so I'm going to say we're looking for mass, so I'm going to ignore the top part and see the bottom part. Those two things are multiplied together. Mass is density times volume. If, say, we were looking for volume, I'm going to put my finger over the volume, and I'm going to say that volume is mass divided by density. Or, if, say, I was looking for density, I could ignore the density and say that density is mass divided by volume, which is kind of fun. I like my little density triangle. In this case, I am looking for mass, so I'm going to put my finger over mass and see density times volume. And all I got to do is 1.25 quarts times the volume, times the density is 0.785 grams per milliliter. But this is a problem. Do you see the problem? It's the units. The units are the problem. So what I'm going to have to do is convert my quarts to another volume unit, like let's say milliliters, so that I can then multiply and get my units to cancel out. So now let's look at converting quarts into milliliters. We have 1.25 quarts of isopropyl alcohol, and we want to turn those quarts into milliliters. Remember, you do not have to memorize these, you just have to know how to look them up. I can go from quarts to gallons, or I can go from quarts to pints. I'm thinking I'm going to go to gallons instead of pints because I also see gallons with liters, and then from liters I can turn it into milliliters. So let me go from quarts to gallons, gallons to liters, and then from there I'm going to go to milliliters. So let's see. Oh wait, there's my milliliters. I found them. They're right there. Milliliters to centimeters cubed. So starting with quarts, going into gallons, there are 4 quarts in 1 gallon. Then I'm going to put gallons on the bottom, and I'm going to turn it into liters. There is 3.79 liters in a gallon. And then finally, liters to milliliters, there is 1,000 milliliters in 1 liter. And a milliliter and a centimeter cubed are the exact same thing, so you can leave them as milliliters, or you can turn it into centimeters cubed if you want. That part doesn't really matter. So 1.25 divided by 4 times 3.79 times 1,000 gives me 1184.4 centimeters cubed. So now going back to my density, looking for my mass, I'm going to go density times volume. So I'm going to go 1184.4 times my volume, times my density, which was 0.785, gives me 929.73 grams, because now my centimeters cubed will cancel with my centimeters cubed and I'll be left with grams. Last step is to look at significant figures. I've got 1.25 here as 3 significant figures, and 0.785 is 3 significant figures. Within my conversions, all of these are definitions. Every one of these is a definition. Every one of these is infinite significant figures, which is well more than, say, 3 significant figures. So my final answer is going to have the least significant figures, which is 3. So my density is going to be 930 with a decimal point at the end to make sure that I've got all 3 of those as significant figures. All right, last but not least today, let's look at temperature. For these temperature scales, you really only have to memorize the Kelvin to Celsius scale, and that is plus 273.15 to the Celsius to get to Kelvin. It also just might be useful to know your Fahrenheit, which is 1.8 times the Celsius. Adding 32 gets you to your Fahrenheit. So let's just say, in July of 2022, the town of Coningsby in England recorded a temperature of 40.3 degrees Celsius. How hot is that in Kelvin? So take your Celsius plus 273.15 equals 40.3 plus 273, 313.45. Now, usually we just kind of ignore the 0.15 here. For significant figures purposes, we usually just leave it as 273. It's fine depending on what type of math that you're using. A lot of times just the first part of your number is important, but you can keep the 0.15 if you want. Either way is fine. And then how hot is that in Kelvin? Fahrenheit. 1.8 times 40.3 is 72.54 plus 32 is 104.54. I'm going to give myself 3 significant figures for that one. So let's just call this 105 degrees Fahrenheit, which is excessively hot for England. Maybe not for Texas, but for England, that is way too much. All right, so that was density and dimensional analysis and temperature, and I hope I'm going to see you guys again next time. Have a great day.